Hello, welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video, we continue talking about parallelism and multi-threading, but we're going to move away from Java and talk about Scala. So, as you've probably noticed at this point, parallel and multi-threading is something that even if it's easy to write code that creates a bunch of threads, it can be very challenging to do it correctly and to avoid the problems that come along with it. And things like the Java util concurrent library made it easier to do in Java, but the creators of Scala really wanted to add additional options for parallelism that take it even further and that make it even easier to work with. And the first one of these is the parallel collections. So here in the Java API, or in the Scala API, there are various packages for collections. And so for the most part, we have been working with either Scala collection mutable or Scala collection immutable. There is also a Scala collection parallel. And as the name implies, things that are inside of this package do their work in parallel. So they have the same methods that you're used to, the ability to map and to filter and do a for each, but instead of doing them sequentially, they do them in parallel. And this has to be a separate subtype simply because people would write code, the code you've written before, when you do something like a for loop that counts from 1 to 10, you assume those things are going to happen sequentially and in order. However, if you do that exact same thing on a parallel range, they will not necessarily happen in order. So this package has a number of different classes that are inside of it. Turns out that to get access of these, what you normally do is you call the par method on a let's go ahead and pull up Scala. So all of your normal sequential collections have a par method on them, and you can see here that when you call the par method on this range, you get back a par range. And so for the par range, all of the normal methods that you're used to don't happen sequentially, they happen in parallel. Let's say we can test this. Whoops. It's not clear to me that that'll work. That this will come out of order. Turns out that printing individual numbers is a little bit too fast. We need to do something to slow this down a little bit. It's also worth noting when you have a parallel sequence that you can call an SEQ method to get back to a normal one. You can call par on things other than ranges as well. So for example, if you have an array built however you want, clearly the array from 1 to 3 is probably not worth doing in parallel for most operations, but this gives you back a par array. What about a list? Well, turns out calling par on a list doesn't give you a par list because lists are inherently non-parallel. In a few chapters, we're going to look at the exact structure of what is behind a list, and you'll be able to see that lists are inherently sequential. You have to go through them in sequential order. So there isn't a parallel version of the list. Instead, there is a par vector, which if you happen to make a vector type and call par, you also get the par vector. Going from a range to a par range, or an array to a par array, or a vector to a par vector, those all happen in order one time. So it doesn't matter how big the array is, or how big the vector is, or how big the range is, they will all convert to the parallel form immediately. Because the list is inherently sequential though, when you call par on a list and it converts it to a par vector, it actually has to go through order in work. So this is a reason if you're going to be doing a lot of parallelism, lists are not necessarily the ideal data structure to be working with. So let's go back into Eclipse and back into our multi-threading example. We already have a Fibonacci here. And we wrote this code to calculate the Fibonacci's with an executor. So let's write a version to calculate the Fibonacci with a parallel collection. And this way we'll be able to compare these two methods. If I just wanted to print it, I could do for I in 30 to 15 by -1 dot par, and then print line the fib of I. And if we change this to using the par collection version, and I run this, you can see that indeed that was all that was needed to calculate these Fibonacci numbers out of order. How many threads is this using? Well, you can tell the parallel collections how many threads to use. We're not doing that, so it's making an intelligent use of the number of cores that I have on this machine. The Java virtual machine can tell how many cores you have, and so the libraries will delegate threads accordingly. That was really easy. Of course, down in this example here, we wanted to actually print our values. So for that, we would need to do a yield. And I need this so it doesn't print them. We'll actually make it so our code looks like that below. And I'll put inside of here the calc. Okay, so we have this version, if I put a quote instead of parentheses, this version is printing out when they are calculated, and this version prints out all the results from there. Now, you might find it interesting to see that, okay, so they were calculated. Let's expand this. They're calculated, and they're always calculated out of order, but my printing even went out of order there at the end. And you might ask, well, what's going on with that? You didn't say to do that. Well, when you call yield on a for loop, it gives you back a collection that is of generally the same type as what you passed in. So this is a par range, which means that values, and in fact if I hover over it, you can see that values has the type par sequence. Okay, so values itself is parallel, and therefore when I call the for each, this is going to happen in parallel too. If I want to make sure that they are printed out sequentially, I can call the seq method, and now we run it, and you can see the calculations happen in an arbitrary order, but the final printing happens in the order from greatest to least, which is the order that we had them on the calculations. So that's a simple example of using parallel collections. Basically, anytime that you have something that you want to be data parallel, you can use parallel collections. You do have to be careful. If I were to have some var declared out here, and then I assigned values to it inside of here, we'd run into problems. Okay, if I mutated it, because then I would have multiple threads mutating a shared value, and the race conditions that apply in all other forms of multi-threading will apply here as well. Okay, so you do have to take a little bit of care of what you put inside of your loops when you're dealing with parallel collections, but it makes it very easy to spawn things off across multiple threads, and you can compare the length of this code to the length of this code. If I weren't printing out the calc, this could get remarkably short. It would be yield of fib I, and that's all it would take. What I'd like to do in the next video is come back. We're going to write a slightly more significant example. We're going to calculate and display a fractal, and we're going to make it big so that it helps to break it across multiple threads, but instead of manually breaking it across multiple threads, we'll use the parallel collections to make it easy for us.